He is adjusting.
Okay.
The next speaker is Faisal Safi. You, right?
Yeah.
On behalf of students 1, Abdullah Sainal Ibrahim. The title of the lecture is Precoding and Testing Technique for Interfacing Neural Networks Associative. Right. University of Malaya, Department of Physics. Please.
Yeah. Thank you very much. Appreciate Mr. Chair. So, good afternoon, everyone. So, my name is again Faisal Safi. I am a faculty member of the Electrical Engineering Department of UAE University. I used to be a student of this guy, Dr. Wan Abdullah, and co-supervised by Dr. Zainul Ibrahim at the University of Malaya. At that time I was working on neural networks, and my area of expertise, or my research, is basically in biomimicry, intelligence, extraction and implementation. Both at the image acquisition system, basically cameras, so I'm working in intelligent cameras, and in every single way of technology possible. So inspired by the neural networks, I got inspired into artificial intelligence in general, and I will talk about that in a second. So today, this is my outline. I'll try to talk about why associative memories, and what is the pain that we are trying to address with this kind of technologies, and what we suggest to resolve that pain. Okay, and for that we suggested the precoding and testing technique, and we applied that into an application which is the bidirectional associative memory. It's one of the intelligent memories that we have. Then we'll present some results in discussion, then we'll conclude, and then we thank the audience for being present. Anyways, so why associative memories? Memory is a very important component of an artificial intelligence system. And what we mean by artificial intelligence system is a mimicry, is an extraction of the biological neuron. Okay? Without memory, there's no intelligence. Period. So that's basically the first part of this. And what do we mean by intelligent memory? A memory that is intelligent is a memory that takes the content itself as an address, not like we do it in the computers, like we give a number for certain information, which is the address. Okay? So intelligent memory is the memory that is content addressable memory, CAM. Okay? For those in neural networks, they know that. It's a well-known thing. It's been a while in literature, but I just want to address that to show you where I am really working. Okay, having said that, the name of associative, where does it come from? The associative is basically also is inspired by the human or biological intelligence, because memory does not work by itself. It always associates with others. So if there is memory, there is associated with that memory. For example, looking at the sea, what you associate with that is the sound of the waves, for example. So when you hear the sound, automatically the image will come to your conscious. Okay? Things like that. So basically, the memories are linked to each other. That's why we call them associative memories. So, two features, content addressable and associative. So that's basically the area of this work. Okay. What is the pain? What is really the pain of the content addressable memories? So, associative memories actually they are a kind of recursive neural networks in which basically the input generates another input, goes at the output, and the output gets feedback to the input, and so on and so forth. So the neural network will relax at the end, basically it doesn't change anymore. And when it does that, so basically it falls into two categories. It may fall into a local minima that is really that could be a local minima that could be spurious state, means it's where the energy of the system, because this is part of actually if you heard about spin glass networks, also suggested by Hopfield long ago. So basically it is a local minima of the energy of the neural network, but it's not a memory. So that's what we call spurious state. A spurious state is a local minima that, yes, satisfy that the energy is at the minimum, but it's not the memory itself. So it's not what we are looking for. So that's the pain, okay? What we are looking is, we are looking for a global minima, a minima of the energy of the neural network where it is not corresponding to spurious. It corresponds to an information that we have stored in the synaptics, okay? All right? So the idea now, how do we find how once the neural network reaches a minima, how can we say this is a local minima or global minima? That's exactly the pain. That's exactly the pain. So how to address that? That's what we are trying to suggest in this presentation, okay? So we want to check if the memory that we, or the minima of the energy that we achieve with this content addressable memory, it corresponds to a global minima, that is a memory, not a spurious state. Okay, so that's the pain. What we suggest is a technique that we call it a precoding testing technique. So this technique has about 5 steps. You know, the input can be continuous, can be binary. We choose the binary one because it's easy, okay? So we check, we take the memory that we want to learn our neural networks. We use the Hebbian rule actually for this one. Again, this is a Hopfield network. So we take the memory, a digitized memory, and we create a code for it using a cyclic code, okay? And then, that's the first step. The second step, the generated code that we receive, that we generate out of this memory, that we learn our neural network, we add it to that memory. And then we learn the neural network, okay? So now, we don't store the memory itself, we store the memory and the code. And we'll see why. After we stored all the memories that we want in the neural network, in the associative memory, we now use it. Because in the content addressable memory, we have 2 phases. We have the learning phase, or storing phase, and the processing phase. The processing phase means the application. I want to use it now. I teach you, now I want to use you. So in the processing phase, what do? We input any information to the neural network, to the associative memory. By the way, until now, we don't know what does it look like. I will show you in the application, it becomes more visible to you. So we let the neural network, the associative memory, run its course and try to get me the memory that is closest to my input. It's like, for example, I get you a picture that I store many pictures, for example, of the whole audience, and then I give you a partial information of an image of one of the audience. Now the neural network is supposed to process recursively this input to achieve the memory. So we let it then process until it achieves its memory. Then we have to detect either it's a spurious state, means no, it's not a global minima, it's not a memory, or it could be the global minimum. So we let it do the job. Once it's stabilized, what do? We do now the reverse. So basically we take now the output, which is the stable state of this content addressable memory, and then we know what is the code and what is the memory that we want to store. So now we take that memory and then we process it. We try to code it. And then we compare it to the code segment of that memory. Now, if the code is the same, that means yes, the recall is correct and it's a global minima. There is no question. because the code corresponds to the data. So that's a successful recall. If not, it's a spurious state. That's it. So these are very simple 5 steps of the technique that we suggested. The application. For the application, we use one of the most beautiful, in my mind, content addressable memory that's called bidirectional associative memory. It has basically 2 layers of neurons, as you can see. Sorry, I have the, forgot that I have a nice tool in my hand here. So it has basically 2 layers, the X layer and the Y layer. Each layer is composed of certain number of neurons. And every neuron in this layer is corresponding, it communicates with all neurons in the other layer. Okay? So basically, if you take it like a sound and picture of the example I gave you for the analogy of associative memory, you can take this as the sound information of the beach. Okay? And this is the picture of the beach. Okay? So in a nice recall, basically if I give you just little tone of that music, when this dynamics relax and stabilize, equilibrium reach, the sound will recall the full sound and will recall as well the image of the beach. Okay? In a very simplistic way. Okay? Alright, so this bidirectional associative memory, so first, before you use it, you have to teach it, the learning phase, by programming all the synaptic strength of every neuron with every other neuron on the other layer. Okay? And we do it with our technique, the PTT, the Precoding testing technique. Okay? So this is basically the content addressable memory that we want to use as an application for our technique. Okay? Just to, it's worth noting that this nice network was actually devised by Bart Kosko in the 1980s. Okay. All right, and then we present our results. So basically, as you can see here in this axis, we have the it corresponds to the humming distance in the x-axis, and in this axis, it's the humming distance on the Y layer. So this is the input layer, or let's say the sound layer, and this is the image layer, if you will. Okay? The humming distance, I'm sure that most of you know, but it's worth repeating. The humming distance is basically measured the dissimilarities between two data. Okay? For example, if you have, for example, a vector of 8 bits, for example, and you have another vector that is the same except 2. So the humming distance would be 2. Okay? So basically you add the number of bits that are dissimilar. So it shows the dissimilarity, the difference. Okay? So as you can see, so here, so we basically we took the memories, we precode them, we inject them in the neural network, we program the synaptic strength, and then once we're done, we tried randomly the input. Okay? So let me go back. That was a mistake. Oops. No, this way. Go back. There's some typo here. Okay. So what happens here? How do we explain the results here? So as you can see here, the green area here is a very close matching recall. So if here this area and this area is green, that means this corresponds to the success rate. So the success rate is higher when the humming distance with the X is very, very small, or actually is extremely high, almost 100%. Why? Because this is another feature of the content addressable, because when we store data or an image, it's not only store the image, it also stores the reverse of that image, which is quite interestingly for this kind of neural networks. So if you record the image or the inverse, it's the same thing. Okay? So that's why the success rate here is actually quite high here, as well as here. Okay? And it's low in the middle. Why? Because it's actually the farthest distance from the full recall. So that's why you find the success rate is quite small in the middle region because I'm too far from the image and to the reverse of the image. Okay? And of course, the complementary of this or the complementary of this would be the failure rate. So that goes without mentioning. So basically 100% minus this will give you that. Okay? So, very nice. And this is only when we store only 4 memories. Let's see when we store more. When you store more, things get degraded. Now we are getting to the blue. Okay, we are getting to the blue. Why? Because, as you know, the content addressable memories, like the biological memories, have a limit, have a capacity. We cannot store indefinitely. We have a certain capacity. Unfortunately, it's small, but I'm sure that some progress can be done to increase that. So as we increase now the number of memories, now the success rate, even at the borders, goes down and the failure rate increases. Okay? That makes sense. And the last one, basically, we are getting now to the 50s, basically, when we store actually 20 memories. Okay? Now we are really in a bad shape in the recording. Why? Because we are approaching the limit. And yeah, so basically here, for the neurons, I think we used, how many? I think about 28 bit on one layer and 22 bit on the other layer, basically. Okay? So, in conclusion of this technique, so basically this technique has a very low probability of error when the Hamming distance between the input vector and any of the stored memories or their inverse is small, as we said. As the Hamming distance increases, the record will go down. That makes sense. It's very expectable. When the Hamming distance grows higher, of course, the recalling of stored images or memories was also smaller, and the error, of course, goes higher. And of course, as I said, as we increase the number of memories that we store into this content addressable memory, the success rate also fails because the problem that this memory has capacity like our own memories. We cannot remember everything. Okay? And actually, this technique, correct recalling means for 100% recall success rate, it follows very, very closely the capabilities of the bidirectional associative memory. So it does not really enhance much, but it helps the machine to know whether the memory is a global or a local minimum, or if the memory is the output of the content addressable memory is a content that we can trust or we can ignore, which is very important because unless we have this is like a checking techniques of the output. If we don't have a checking techniques, we cannot know whether our data is correct or not. Okay. All right. So next. Oops. All right. Oops. That's one. All right. Thank you very much, and that concludes my presentation.
Okay. Please.
I have 2 questions.
Go ahead.
Please go back to the slide where is the where 4 memories. Yeah.
This one?
No, next one.
This one?
No, next. It's previous.
Oh, okay. Next. This one.
Yeah, that's one.
Go ahead.
Why do we have the 2 violet, like 0 to 10% regions? Like there are 2 areas which are violet.
This one's?
Yeah.
So basically, this.
Why is in the middle? It's not the worst. Why the worst is something close to.
No. The worst is actually. Yeah, you're right. Actually, I cannot explain this. Yeah, you mean like this one?
Yeah.
This looks like deeper compared to this one.
Yeah,
that's interesting. I don't have an answer for that. That's definitely a good one. But it's not really because neural networks, they are not really a perfect thing. Still, there are things that we do understand and some things that we don't understand. This falls in my black side, okay? So I'm not sure why it is a little bit higher in here. That could be due to my random data that I put there. Maybe it's not perfectly random. And also the difference is not that huge anyways. So it's very minimal. So you can say this is a noise.
All right. Okay, so that's enough.
Yeah.
But
So
it
because
doesn't
the
seem
difference
like
is
a
not that
noise.
high,
But
you know.
it's very regular to be a noise. No.
What's that?
It doesn't seem like
Could be, yeah. It's debatable for sure. As I told you, it's in the black side. If I know, I would told you.
Also, there is this cream color, which is not.
I mean, this, yeah.
No, between the green and the.
And the blue? Yeah, there's some
Yes,
cream,
there's also
but it's
this-
not in the legend.
It's also. It's not. It has nothing to do with the discretization that you have.
No, it's not due to discretization. This could be because of the data that I used or something like that, you know. It's not perfect, but the profile overall makes sense actually. You understand? So the correct recall would be close to the image or its inverse and be worse when you are in the middle, in between basically. So that's the thing.
You had a second question, right?
Yeah.
No, what's your second question?
Did you try, like it's about amount of memories that you can store with this approach, but did you try like bigger, deeper networks or more layers to store more memories or to approach bigger data?
Yeah, that could be. I didn't try it, but that would inspire me. Yeah.
Something that very natural pops up into mind when you want to increase the capacity, right?
Sure. That's a very
Oh,
good
you just
suggestion.
do that.
Yeah, that's a very good suggestion. It would make sense, absolutely. Here we are just suggesting an application. We are not really saying that this technique would be the best for this. No, we can improve the memory recalling of the network, definitely, by adding multi-layers there, by doing more stuff. Definitely, we can increase that. But the point is not that. I'm not emphasizing on the memory capacity. I'm emphasizing on the one thing, very important in here, which is the capability to detect whether the memory is global or local minima. That's all what I'm looking for. But in terms of like improving the memory capacity, definitely there are techniques like what you suggested to add more layers or to do more about the neural network itself. So if I would make it short as an added value of this contribution is basically I want to give a tool to the machine to detect or to know whether the stable state of the content addressable memory is global minima or local minima. That's all what I wanted to do in this contribution. But to increase in capacity, we, as you said, tons of techniques.
Okay, thanks.
Thank you.
Senator, please.
What are limit of memory? To bit per synapse more.
I beg your pardon?
What are limit of this memory?
What's the limit?
Yeah. Actually, here for this memory, the neural networks, the content addressable memory, and the RAM in particular, they have actually the traditional one, like the just 2 layers. I think, if I'm not mistaken, is about 27%. Like, for example, if you have 100 neurons, the maximum that you should get, if my memory is not, bad, so it's about 27 maximum that you can store. So it depends on the number of neurons. The more neurons you put, the more memories you can store, which makes sense that we have actually billions of neurons, and we can remember stuff. So over the years, still the capacity will be there, but we will lose something to put something in you, and that's about it. So it depends on the size of the network. Okay, the higher, the more, but the capacity ratio would be almost more or less the same. Okay, but again, as the gentleman suggested, if we do change the network, like adding a hidden network or some other layers, we may improve the capacity, definitely. But again, it will be limited by that number. But the only thing I wanted to put in here, I emphasize it again, is basically give the machine or human a detection mechanism by which to know whether we have the stable state is really a global minima, is memory, or just a spurious state that we need to avoid. By how? By changing the input, basically shaking the input somehow, changing some bits to get it off the minimum, okay, and go to the global minimum. Something like that. Yeah. No problem.
So the question? Yes, please.
Do you know the HNN, Hopfield neural network? network.
Yes.
Also, we use the memory, you know.
Yes,
The
yes.
state point. So what's the difference between here?
The state points. So
Yeah.
basically, the state points are the memory itself. Like for example, if we go, what I mean by that
You
is
mean, when you say memory, you mean pattern, right?
pattern. Yes,
Oh, okay.
Sometimes say memory, but he means pattern.
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 Yeah, that's what we mean. That's the pattern. That's what I mean by the memory. Yes.
Okay.
Yeah.
But, okay, is that some other question? So that was a bit confusing, and all the time during your lecture you say memory, and we didn't understand, but I realized that you meant pattern.
Pattern.
So
Yes.
So pattern, right?
Yes. Yeah. In fact, we store the memory, as you said, in the synaptic strength. But what we get is actually the pattern that we can see here and there.
Yeah.
That's basically the thing that we record. But when we code it in the synaptic strength.
The whole is the memory or associative memory, but you store certain amount of patterns.
Yes,
Okay.
definitely. Yeah.
Right. So this attendee left, but it was a very interesting suggestion, and I will suggest you that you take serious, because if you know the autoencoder of Hinton in deep learning, right?
Yeah.
You can retrieve a noisy image. You know, you can enhance the quality. So, but here, as you said, I feed with the sound of the seashore, and I recover the image. Right? You are relating different patterns.
Yes.
But again, you can be inspired by the autoencoder of Hinton and put layers. Even though that you won't recover the input, you will recover something else. But there is a mapping between two. It could be very, very interesting.
Absolutely.
You know?
Yeah.
So-
Yeah, definitely.
Now, he said also, what I also wanted to ask, in the case of the Hopfield neural network, you have also the course of dimensionality. That means you have a certain amount, depending upon the neurons, you can store certain amount of patterns. Right?
Yes.
And here's the same. But why is the difference that you guarantee global minima and Hopfield got spurious?
No. The spurious state is basically a possible state of the system of the neural network to relax to. Means to relax to. That means it will not change
And
because it's
Hopfield-
recursive.
Hopfield
the same thing.
get trapped in the spurious?
Yes, of course. Hopfield network
And
also
this
suffers
no.
from the same.
This no.
No, both of them. The neural networks, when they are used recursively,
Right.
basically as a memory,
Okay.
basically, they fall into two minima. Either a spurious state,
Okay.
where basically the neural network will not change its states.
Yeah.
So basically, it will not change. The input is the same as output,
Right.
and will stay forever there.
Yeah.
Or it's a global, so also the same story, it will not change. But one of them is actually correspond to memory that we programmed,
Yeah.
we learn,
Yeah.
and the other one does not. It's just a local minima that we need to get our system off in order to reach the global
Yes,
minima.
but this I don't understand very well. When you are falling in this attractor of the spurious,
Yes.
how you get out of this?
Very good question. Very good
How do
question. So what do they do? So basically, as a human ourselves,
Yeah.
when we reach, for example, a memory that still is stuck on us, on our brains,
Right.
but we are sure it's not. We know that it's not. Why? Because it does not make sense to us somehow.
Oh.
So what do? We change that. So we kick that minima. We push the network by changing or flipping some neurons out. So basically giving an energy to the neural network to get off of that local minima and search something else.
So this procedure PPT means when the Hamming distance is not low, then I kick, so I put energy to get out of this attractor, right? That's your algorithm. Right?
Not quite, actually.
How you do that?
So the algorithm is not to push the neural network out of the story state to a global minima. No, the algorithm that I suggest is basically to tell the user who is using this network, hey, this does not correspond to a global. But as a user, if, for example, this is an error, okay, that's the
can
next
change.
stage, then the user will say, okay, fine, I will change the input here, I will kick the network out until I will get the